The question of whether it is possible to break the light barrier has been troubling humanity since the first ideas about interstellar travel. Einstein's special theory of relativity, 1905, imposed a strict limitation. Nothing with mass can move at the speed of light, let alone exceed it. However, in 1994, Mexican physicist Miguel Alcubierre proposed a solution to the equations of general relativity, GR, in which an object can move faster than light without violating these very laws. This solution gave rise to a term familiar to science fiction fans: warp drive. The hypothetical technology that allows travel faster than light by distorting space has become the subject of both serious scientific debates and endless fantasies about the future of astronautics. One of the most striking features of general relativity is its flexibility. Einstein's equations allow for many solutions that describe all sorts of space-time configurations, from an expanding universe to black holes and gravitational waves. Some of these solutions are physically realizable, while others are not. In 1994, Alcubierre published a paper showing that it is theoretically possible to create a local distortion of the space-time metric in such a way that an object inside the bubble of the distortion moves faster than light relative to an outside observer. The object itself remains stationary inside the bubble. It is space that moves, not the ship. How does a warp drive work? In the classical view, a warp drive creates a warp bubble, a region of space where the front of the bubble compresses space and the back stretches it. The ship finds itself in a flat, uncurved region inside, not experiencing acceleration, but moving along with the bubble. The model resembles the analogy with a carpet. Instead of sliding along the surface, the carpet itself curls up, and you are transported along with it. It is important to emphasize, no laws of physics, including the limit on the speed of information transfer, are formally violated. This is the movement of space, not an object in space. The biggest challenge facing the warp drive concept is the need for negative energy. To bend space into the desired shape, exotic matter with negative energy density is required. Such matter does not exist in conventional physics. According to Alcubierre's own calculations, creating a bubble several hundred meters in size would require negative energy equivalent to the mass of Jupiter. This makes it impossible to implement even in theory. Later, in the 2010s, Dr. Harold White of NASA's EagleWorks proposed modifications to the metric that would reduce the energy requirements by 17 orders of magnitude, but even then, they were still astronomical. NASA did not ignore Alcubierre's ideas. In 2012, the Advanced Propulsion Physics Laboratory, known as EagleWorks, was established at the Johnson Space Center under the direction of Harold White. The EagleWorks team worked on both theoretical calculations of modified metrics and experiments with electromagnetic structures that could demonstrate at least a local curvature of space. One of the most discussed results of EagleWorks was an experiment to observe microscopic warp effects in a resonance chamber, EM drive. These data were repeatedly disputed and later refuted in peer-reviewed publications. Nevertheless, this was the first time that a government space agency officially supported research in the field of warp drives. Even with exotic matter and the necessary technology, the warp drive comes with a number of fundamental problems. Radiation cascade when stopped. A warp bubble is calculated to collect particles and radiation at the front. When stopped, all this energy is released, possibly in the form of a deadly front. No control. It is impossible to send signals outward from within the bubble, making navigation virtually impossible. Bubble stability. The slightest external disturbances can lead to the destruction of the metric configuration. Causality and time paradoxes. Some forms of metric lead to the appearance of closed timelines, time loops which create philosophical and physical paradoxes. Interstellar travel is discussed in the context of various concepts. Wormholes? Theoretical tunnels connecting distant parts of space. They require even more unstable forms of exotic matter. Generator ships, spaceships, on which generations of people change over hundreds of years of flight. Cryogenic freezing, freezing passengers for a long time. Laser acceleration of sailboats, breakthrough starshot. The concept of small probes accelerated by lasers to 20% of the speed of light. More realistic, but still extremely complex. Could a warp drive ever be built? From the point of view of modern science, no. Too many ifs, too little evidence. But the warp drive, like the idea of flying to the moon a century ago, remains a symbol of humanity's quest to overcome limitations. Even if the Alcubierre metric never makes it off the page, research in this area is stimulating progress in quantum field theory, general relativity, cosmology, and astrophysics. The idea of a warp drive is at the intersection of mathematics, theoretical physics, and philosophy. It is both an impossible dream and a growth point. Theoretically, it is possible. In practice, it requires knowledge, energy, and materials that are not available today. Nevertheless, the very fact that such a solution to Einstein's equations exists is a reminder. The universe is still full of amazing possibilities. Who knows, maybe in centuries, an idea born on the pages of science fiction and equations will become what brings us closer to the stars.